In preparation for our lab on the 29th, we're going to talk about soil porosity and density. So there are several important physical properties for soil. They include soil color, soil texture, soil structure, and soil density and porosity. And I've posted some readings on soil color for you. Surface area has a lot to do with porosity. Clay particles have thousands of times more surface area than silt particles, and it also has hundreds of times more surface area than sand particles. Okay, here are some just general influences the soil separates have on properties and behaviors of soil. So just kind of going down the line here, I'll just pick out a few. Of course, water holding capacity in sand is very low, while in clay it's very high. Aeration, very good in sand, poor in clay, and of course silt is always going to fall somewhere in the middle there. Resistance to pH change, which is really important when you're dealing with pH that is not adequate for your plant material. Sand has a very low resistance to pH change, while clay has a very high resistance, which makes sense because of cation exchange capacity, which we will talk about later on in the quarter. So plant available water is the water that's loosely held on particles, surfaces that is accessible to plants. Unavailable water is held close in particle surfaces or in micropores. So field capacity is the water that is left in the soil after gravitational water has left. That's your plant available water. Field capacity is where you reach saturation and water will leave gravitationally. Permanent wilting point is the point where plants can no longer get hold of the water. There's always going to be a little bit left in the soil. And you can see that's directly correlated with the clay percentage. The more clay you have, the more unavailable water there is. So here we've got saturation, and then you've got the gravitational water coming through. Field capacity is where you've got a lot of water there. That's your plant available water. And then the wilting point, it's hard to see on this picture, but there are some gray areas right around the soil particles. That's unavailable water that is always going to stay in the soil. So soil structure is the arrangement of sand, silt, clay, and organic matter in soils. They form structural units called PEDs or aggregates. The size or class of the PEDs are described as fine, medium, or coarse. So here we've got a picture of soil particles. They aggregate to form a PED, and then the PEDs are stacked around each other to form structure. Granular structure resembles cookie crumbs. It's usually less than 0.5 centimeters in diameter. This is commonly found in surface horizons, and we'll talk about horizons as we talk about soil classification, but this is basically where the roots have been growing. Blocky structure, these are irregular blocks that are usually 1.5 to 5 centimeters in diameter. They can be subangular or angular blocky, and those are going to be a little bit lower in the soil. Prismatic structure, these are vertical columns of soil that might be a number of centimeters long, usually found in lower horizons, and you can see where the arrow is pointing. That is your prismatic structure. Columnar structure, these are vertical columns of soil that have a salt cap at the top. This is usually found in soils with arid climates. Platy structure, these are thin, flat plates of soil that lie horizontally. This is usually found in compacted soil. And as you can imagine, water is going to have a hard time getting through that. Single grain structure is soils that break into individual particles that don't stick together, usually in a sandy soil, usually has a very loose consistence to it. Massive structure, this is soil that has no visible structure, is hard to break apart, and appears in very large clods. And so you can see structure can affect water movement. Massive, very slow water movement. Platy, very slow water movement. Single grain, you're going to see very rapid. Granular, very rapid. Blocky and prismatic are going to have moderate water movement. And we're going to get much more into water movement further on into the quarter. So altering soil structure, unlike texture, you can alter the structure by tillage or traffic. This breaks down your natural structural units, and this can happen when you're tilling your soil that are too wet, or you're compacting soil with heavy equipment. So breakdown of aggregates occurs when you have a loss of organic material. That is usually associated with the loss of microbiota. Tillage and rain can also cause this. So tillage and aggregation, this is when you physically break the aggregates apart. What it does is it stirs air into the soil, which stimulates your microbes, and that increases the rate of organic matter decomposition. So your soil organic matter is lost to the atmosphere as carbon dioxide. And so this can result in less organic material, and without organic material, you don't have the glues that bind the aggregates together. Macropores are quite large, and they allow ready drainage of water and air movement. And some of the smallest roots can move through there, and a multitude of organisms. So the spaces between sand grains are often macropores. Micropores are really quite tiny, and they're usually filled with water. Water movement is very slow, and this is the water that I was talking about that's unavailable to the plants. It's held too tightly to the soil particles. So with the power of clay-sized particles, if you add a little clay to sand and they start filling the big pores, dividing them into smaller ones, water will be held there, and it'll be difficult to get that to your plant material. So porosity is the volume percentage of the total bulk not occupied by soil particles. Permeability is the measure of how easily water flows through the soil. So they're not necessarily the same. You look here, we've got well-sorted sand and gravel. Porosity is 25 to 50%. It's very permeable. The water's easily flowing through there. If you go to the clay here, it's going to have more porosity because it has more surface area, but it's going to have low permeability. So bulk density, which we'll be doing in lab on the 29th, bulk density is the mass per unit volume of dry soil. This is the amount of solid material packed into a particular volume. So the lower your bulk density, the lower the weight, the more pore space. The higher the bulk density, the higher the weight, less pore space. So you can see here this is associated with soil particles, with clay. We've got a low bulk density, but pore space is high. Sand, if you go all the way down here, we've got a higher bulk density, but we've also got a lower pore space. Okay, and here's some different bulk densities for plant growth in sands, loamy sands. You want to have it less than 1.6. Once you get to 1.69, you're going to start affecting root growth, and bulk densities above 1.8 are going to be restricting root growth. So normal soils would be 1 to 1.6. And some people bring in soil that has quite a bit of organic matter. When we do this bulk density test, you may actually be under 1 for your bulk density. And you can see once you get between 1.4 and 2.3, that is considered brick. And 1.7 to 2.2 is commonly found in construction sites. So bulk density totally affects how your plant material behave. So soil bulk density is the mass per unit volume of soil that's been dried to a constant weight at 105 centigrade. So bulk density is the weight of your dry soil divided by the volume of dry soil. And we'll do this in our lab. Okay, so the plow layer is the upper portion of the soil. That's where your roots are going to be. You can see, hopefully you've got a fairly low bulk density in your plow layer, but as you go down, you can see it gets larger, and so very, very compacted. Particle density is the mass per unit volume of soil particles. So particle density is a relatively constant parameter and is sometimes assumed to be 2.65 grams per centimeter squared. So particle density equals the weight of the dry soil and the volume of the water displaced. We'll be doing this in lab. Soil porosity is the percentage of a soil that has pore space or voids. The average soil has a porosity of about 50%. And the pores are filled with air or water depending on the moisture content. So sands have larger pores, but total pore space is less than that of clays. And if both bulk density and particle density are known, the total porosity can be calculated using this formula, and we are going to try to do that in our labs. So some of the causes of compaction include traffic, of course, heavy pedestrian traffic and vehicles, tillage, which can initially loosen the soil but lowers organic material, destroys structure, and of course tilling when the soil is too wet is particularly harmful. And then rain breaks apart surface beds and tiny bits wash into pores, forming a crust. And so there's three types of soil compaction. We've got surface crusting, and that's what I just talked about. Rain can help form this surface crust. So then you're trying to germinate seed in there, and that's not going to work. And then you've got plow layer compaction. That's the area that should have the roots going. And then you've got subsoil compaction. So the roots are going to have a difficulty, and seeds have difficulty surviving in this setup. So on the left, you've got unrestricted root growth. On the right, you've got compact soil. So you can see it's kind of under wheel tracks. Here's your surface crust, plow or tillage pan just below the plow depth, and deep soil compaction. You can see the roots are not going anywhere. They're just not. So it's really imperative that we try to reduce soil compaction.